Hello, everybody. Thank you for coming on this workshop. We are Carlos and Ignasi, and we work at the protocol team at Polygon. Today, we're going to do a workshop about optimizing the zkEVM throughput. This is the Series 2. We already did a talk about this a few months ago on Brussels, on the SEC. But this one will be like the continuation. But anyway, you can follow, although you were not in the first one. So, first of all the code that we will be explaining and using for the workshop, you can get it from this link on GitHub, from the branch. You don't really need to code during the workshop, but in case after the workshop you want to check it, you should follow this. Okay, the beginning of the presentation will be the same as the other session we did, because it's the one where it's the part where we explain how the zkASM, the language, works. We'll do an overview, we'll explain the register, the instructions, we'll do some examples, and we will talk about the counters, which are the main measure to measure the performance of the zkEVM. After that, the second part, this one is the one that will be different than the other presentation. We will explain two optimizations. Well, first we explain some new registers and new tools that we had on the zkASM to optimize it, and we will do two practical examples. We will see the code before optimizing it and after optimizing it with the explained tools. We will see the optimization of the opcode of push, which is a I think it's the most used opcode in the EVM, and we will also see the optimization of the mloadx and ms.x, which are two tools that are using all along the zkEVM to interact with the memory. But first of all, let's get into the zkASM language. The zkASM language, it's developed in-house. It's a language that looks like assembly. It's used to write a program that it compiles in a way that can be fed to an executor, and after that the executor with this trace, when he's processing a state transition of a batch is a group of blocks and a block is a group of transactions, so it's generating, with this trace he can generate a proof of the state transition of a few transactions. So this language is done like very customized to be the best performance on doing this. The language, as you can see on this image, looks like this. It's very similar like assembly. We will go deeper in this code later. But let me also talk you about the compiler. The compiler is the one that gets the files in zkASM and converts it into a trace where it completely defines each one of the steps that are represented on the lines of code of the zkASM. Now let's check the code. I will go to the build file. It's a JSON file that is the output of the zk compiler of these lines to start with like seeing how the code looks. So I think I'll go maybe even bigger. Okay, so the zkASM, the first thread always starts in the main zkASM file, and these are the two first steps. Each one of the lines is a step. As you can see here, we have a register called step, and with this we're assigning the value of a step to A. As this is the first step, this step register increases by 1 on each one of the lines of the code. So here the step value is 0. And in this second line, we do an assert. An assert is an instruction that checks that the value in register A is the same as the value in the left part of the line of the assert. In case it's not, the execution will fail and the proof will cannot be generated. So here, what we are doing is checking that indeed we are starting the execution from the very beginning, where step is 0. Now let's see how it looks when it's compiled. When you build the zkEVM, it outputs the following file. It's the rom.json, and it's a very long file where it's a JSON, where it has a program with an array and a lot of objects in it. each object is a step. Let's analyze the first step following this first line, where we are assigning a step to A. As you can see, we have the in step. This trace of JSON is the one that is used by the executor. So when he reads this first object of the array, he will know that he has to get as input the value of the register step and set it to A. This one is the flag where it says to the executor, set the register A with the value of a step. And these 3 lines are just metadata that is very useful for debugging. So this representation of the first line is the representation like this when it's compiled. And the same one happens with the same thing happens with the second line, this assert. It represents like this. First of all, we have as input a constant, which is 0, and then we have the flag of assert to 1. It means that we have to do an assert on this step. Okay, this was to do like a first hit up, a first contact with the language and understand a bit how the compiler works. Okay, now you want to continue, Carlos.
Hi. Okay, so hi, my name is Carlos Matallana. I'm going to explain a little bit the language that we use, the zkASM. Ignasi kind of did an introduction of how to use it and show some code examples. And basically, what I'm going to describe right now is the language itself. I will describe all the registers that we do on the zkASM and all the instructions that are available in order to code the zkASM. As Ignasi said, the zkASM language, it's pretty much like an assembly language that you can use, a standard one. But, well, we have different instructions and different registers, and it behaves a little bit different. Okay, so let's first explain the registers. We have 2 types of registers. I would say we have long registers and small registers. The long registers basically are registers that are composed by 8 elements. Each one of those elements is a Goldilocks prime frame number, and basically it's almost 64 bits. And basically what we use, it's only the less significant 32 bits. If you basically join all of them together, you have a register multiplied by 32 bits, you finally have 252 bits, which is the standard operations on the EVM, basically. Why are we using the Goldilocks prime field number? Basically because it's a zero knowledge friendly prime number, so you can do a lot of operations in the environment very quickly when you compute the snags, the hashing, and so on. On the other side, we have registers that only have 1 element. This element is again a Goldilocks prime frame number, and basically, well, yes, it's just, I would say, 1 register that contains 1 element. Okay, now that we know that we have 2 different types of registers, let's say the registers by themselves. So we have 5 different registers. We call it kind of a generic registers, and they are basically A, B, C, D, and you can do with them whatever you want. We'll see later on how to use them. We also have a register which is the state root. As you may know, in the zkEVM, we have we use a sparse Merkle tree, and the summary of this sparse Merkle tree is the root, and basically this register is basically the state root of the state tree. Also, we have the rotate left C register. We will know, we will see later on how to use that in order to do some optimizations. We'll explain later. And then we have a kind of a lot of registers, but those registers are 1 slot register, again, just 1 Goldilocks prime frame number. And those registers are basically all the counters, context, stack pointer, program counter, gas, ZK program counter, return, step, maximum, and hash pos. Here, it's important to mention, I mean, all of the registers, you can be familiar or not, but what is important to mention is that we have the program counter in order to read smart contract bytecode. So we point to the smart contract bytecode, and then we read the bytecode. And then we have the zero knowledge program counter, which is the counter of the program itself of the ROM, basically. Okay, so we saw all the registers that we have available in the assembly language. Now we're going to see all the instructions that we have available that we can use when we code zkASM. The two first ones are, I would say, very typical in assembly language: memory load, memory store. You get some value from the memory and you load it into a register, or you just save into the memory some value that's on some register. Then we support 3 different hash functions, kickack, sha, and posidon. They all have exactly the same structure. And basically, in order to do one of those 3 hashing, you need to use hash-k, hash-k-len, and hash-k-digest. Later on, I will explain in details how to use those instructions, but the summary could be that in the hash-k, imagine that you have kind of a buffer, empty buffer of bytes, and with the hash-k, you are adding bytes to that buffer. With the hash-k length, you are basically closing that buffer, and with the hash-k digest, you get the result. Okay, exactly the same for the hash-p, which is hash posidon. And then, as the other assembly language, you have this kind of a jump in order to jump to another subroutine, and you have kind of conditional jumps. In this case, we have the jump negative and jump carry. But they are, in a sense, they are basically conditional jumps. Okay, I would say that the next 2 ones are for, it's kind of a sugar syntax, because when you are developing on zkASM, it's very convenient. Instead of jumping to a subroutine, saving the ZK program counter, and when you end the subroutine, jumping again to where you were before, instead of that, you can just use these call and return instructions, and I would say the program does it for you. It automatically saves the program counter, and if you just write the instruction return, it will again return to the previous point. Then we have the assert instruction. Just basically, you assert that some value is exactly as other values. And then the next 2 ones are also very important, which is basically the slot and store, and this is basically storage load and storage slot. When you want to read some value from the Merkle tree, from the sparse Merkle tree, you somehow need to use those instructions. On those instructions, basically, I will not get into the details, but basically the key 0, key 1 basically defines the Merkle path to travel across the Merkle tree in order to get the value. And here, exactly the same, but you are storing some value. The value will be stored on registers D, and registers C, A, and B are used in order to travel across the Merkle tree. Then, the next one is the arith instruction. This instruction is basically used in order to do multiplications for 256 bits. And also, in order to prove divisions, you can use multiplication as well. And the next ones are basically standard operations with 256 bits number, which is basically addition, subtraction, less than, signal less than, equal, and bitwise operations. All those ones, from the addition until the XOR, they are basically using what we call the binary state machine. Okay. And this one is outdated. Why? Because we're going to kind of explain how these instructions evolve in order to optimize some of the opcodes. But in order to understand it better, we wanted to first explain very briefly how these old instructions works. This is basically memory align read, memory align write, and memory align write 8. As you may know, in Ethereum, you have 3 different opcodes. Memory read, memory write, 256 bits, and memory write, 8 bits. That's why we kind of did exactly the same instructions, but on the zkASM. Those instructions basically works with 32 bytes, but we have a special one, which is the memory aligned write date, and this basically matches the opcode of Ethereum. We will see later on that this approach was nice, but in order to optimize the code and some opcodes, we kind of did, I would say, a dynamic memory align, where you can select the offset, the bytes that you are reading, and then the NS, basically. Okay, Ignasi.
Now we will go a bit deeper on how the register works, the taxonomy. They are easy to use, but it's true that they have some nuances that we will see now. To do the zkEVM, we have 5 registers, A, B, C, D, and E. Each one of each, it's an 8-element Goldilocks prime file number, so it's 32 bits, so 8 elements of 32 bits, it's 32 bytes to 156 bits. So, for example, yes. If we have A inside, we have these 8 elements that we number them from A7 to A0, from the most significant to least significant. So register assignment, it's very simple. You do it like this, you assign 5 to A. So in this case, from A7 to A1, all the values is 0, and A0 is 5. The same way you can assign the value of a register to another register, like this. So after this step, the value of C will be the same as A. Now we'll try to put a very big number in register B. This is the maximum number that you can do with 32 bits. In this case, as before, from B7 to B1 we will have zeros, and on B0 we will have like the maximum 32-bit value, which is everything Fs. And here is the nuance I was talking about. If we do A plus B, we will be having an overflow because this value it's not expanded to the other elements when you do it this way. So in this case, from B7 to B1, you will still be having 0 values, and on B0 you will have this value, which as is a signed number, it will be like negative. If you really want to do this addition without overflowing, you will have to consume a counter. You will have to consume an arithmetic or a binary counter. So it's very important when you are developing the zkEVM to have this thing in mind, because it can create a lot of problems. You need to know that when you assign some values to the registers will be in some moment greater or not than 32 bits, because in case they are greater, to operate with them you will have to use binaries or arithmetic instructions. Let's go to the next slide. Now I will explain more visually the instruction Carlos talked about, which is the rotate LC. It's very interesting because some optimizations that we will explain later use it, so I wanted to go a bit deeper on it. It's very simple to understand, and it's also very useful when you want to operate with 32 bits in a register, but playing with the different slots of this same register. Let me explain. If in C we have this 32 bytes number, which is very, very big, I have splitted them in slots of 32 as all the elements from the element C7 to C0. So the rotate LC will have the same value, but C7 is put in the position of C0 this way. You'll see the blue one, now it's the last one. This is very useful when you want to apply some operation in one specific element of the register. Now some flow control operations. I'm not going to extend a lot on it because they are very, very simple to understand. Jump n, when you call it, if you put the register that you put at the left of the instruction, if it's negative, you will be jumping. It's like a condition instruction. You will be jumping on this level. But it's important to understand that it's only checking the A0 op. So it's only checking the last 32 bits. The same happened with the jump 0, which will jump if the value is 0, jump no 0, which is the opposite. The jump carry, it's an instruction that it's used, and it will jump to the level when there is a carry on the left operation. And the jump no carry, it's exactly the same, but the other way. We have an example here of jump carry with the lower than instruction. So in case this condition of lower than is succeed, we will be jumping on the carry level, else we will be jumping on the no carry level.
Now I will explain, as I mentioned before, how the hashk, hashcalend, and hashkdigest work. I did an overview. But basically, as I mentioned, there are 3 instructions: hashk, hashcalend, and hashkdigest. And you can imagine kind of a table, okay? A table where at the very beginning, the buffer of bytes that we are going to hash, basically, it's empty. And then we are going to add some bytes over there. So in order to add some bytes into this buffer, we will use the instruction hashk. And this hashk instructions is dependent on 2 registers, hashpos and dregister. And basically, this hashpos and dregisters means hashpos is basically the offset, and d is the size. So at which point do we want to add bytes, and how many bytes are we going to add? And then what we call the OP, which is another kind of input of the instruction, it will be the bytes to add. So for example, in these 3 lines of code, basically, we're going to start at position 32. So for example, this arrow here in the middle. We are going to write 32 bytes. And which bytes are we going to write? Basically, the bytes that are in register A. Then we use the hashk instruction. This E that you can see here is kind of an identifier of the hash. We can have so many hashes open, and we can fill a lot of bytes on those hashes that are open. So basically, the E is kind of an identifier of that hash. Okay, another instruction that is very important, not for the optimizations that we're going to explain today, but it was very important for the optimizations that we spray on Brussels, is the assert. The assert instructions, maybe, of course, assures you that some value must be equal to another value. And this is very important, the must, because if an assert is triggered, it means that the proof cannot be generated. And basically, this is used to verify what we call free inputs. What is a free input? We have it here. Free input is that the prover can provide the value that the prover wants. It is not checked at all. So normally when we do that, it's because we want the prover to provide some value, but then later on we want to verify that that value is correct. And this kind of opens some kind of optimizations that instead of computing some value, you just let the prover to provide the value that the prover wants, and later on you verify. So not compute, but verify. Okay, so we talk about optimizations, we talk about the language, but what are we going to optimize? Basically, what are we going to optimize are the ZK counters. I did a presentation yesterday about the ZK count, what are the ZK counters, what are the ZK counters types that we have on the ZK assembly, and what are those numbers. But very briefly, you can imagine the ZK counters as the gas in Ethereum. It's a resource that is limited on the ZK side. So in Ethereum, you have a unit, which is a block. This block, the resources on this block, on the execution side, is measured in gas, and it's unidimensional. It's only the gas. On the zkEVM, the unit is the batch, and this batch has some resources, which are the ZK counters, and there are many of them, so it's multidimensional. Here we can see that we have 8 different resources, the steps, arithmetic, binary, memory alignment, keycag, Poseidon padding, Poseidon, and SHA-256. Here, it's important to mention that the numbers that you can see here are the available resources that we have in a batch. For example, the steps are basically, you have here about, instead of steps, maybe you have here about cycles or clocks, no, in other projects. So here the steps are each row that you hit on the in the zkEVM. So it's very straightforward. Each line of the ROM, it's one step. So we have plenty of them because it's very, I would say, simple. But on the other side, for example, the keycag state machine, we only have 2,000, around 2,000 keycag state machines available. Why is that? Because the keycag state machine is way far more complex than, for example, the binary state machine or the arith state machine. That's why we have way less resources on this keycag state machine. Okay, so here what we are going to talk a little bit is about all the optimizations that we did on the language itself. Those optimizations came after a deeper analysis on what we can optimize on the ROM. What is the code that is commonly used, that is used everywhere, that we can optimize in a very straightforward way. So we realized that, for example, when we call a subroutine on the zkEVM ROM, inside that subroutine, we needed to use, for example, the arithmetic state machine. And the arithmetic state machine, the inputs are the register A, B, C, D, and E. So what happens is that when we call that function, at the very beginning, we need to kind of save some kind of a snapshot of the values of the registers, do the functionality, and then recover that value again. And this is basically consuming 1 step, 2 steps, 3 steps, 4 steps. For example, here in the example, we are consuming 4 steps in order to store the value and 4 steps more in order to retrieve the value again. So what we did on the zkAssembly side, we introduced 2 instructions in order for just in 1 step store a lot of registers just in 1 step. So that's why we introduced these 2 instructions, save, restore. So instead of using 4 steps, now here we are just using 1 step. But we are calling a new instruction, which is the save. In order to recover those values, we are using the restore. Another optimization, we realized that in the code, there were a lot of lines of code, I would say, wasted, because we needed to somehow loading some variable from the memory into a register and then just do an addition of 2 registers. Okay, this is basically consuming 2 steps, but what if the memory state machine, instead of verifying the OP, basically the OP is I would say, the OP is all that you have on the left side, I would say. And so instead of verifying the OP, you can verify the free input. The free input basically is the dollar here. So this means that basically we can join 2 steps into 1 step super easily by introducing this new instruction. Okay, so internally in the pill we have this introduction of assume free flag. This indicates that instead of verifying the OP, it verifies basically the free input. And this was very useful because it allows us to again reduce the steps used in any function basically. Okay, now Ignasi will explain the memory line.
Another optimization that we did is regarding the memalign state machine. As we've said, the memalign, what it does, it's like verify the correctness of some bytes insertion in the memory. The main problem that we found of the first version of the memalign is that it only supported as an input 32 bytes. So what was happening is that you had like to create this, in case you wanted to insert less than 32 bytes, you had like to create shifting. We will see it also later, like shifting these 32 bytes that you wanted to insert, retrieving the memory that was already stored in the memory. So we add a new feature, a new input to this state machine, which is stored in the register C, called mode, which is like coding some information that we need the memalign to have in order to operate. We can add the offset bytes in case we want to insert in an offset of the slot. Remember that Ethereum has a slot of 32 bytes. This mode is coded in an array of bytes, so the first 64 is for the offset bytes. As you are playing with two sequentially slots, we can make an offset from 0 to 64 bytes. The next one is the length that we want to insert into the memory. And finally, we can also set if you want a left or a right alignment, putting a 0 or a 1 in position 1192. And the same if we want little Indian or big Indian. I'll show you a more deep example now. So to read memory, we need to read the two consecutive addresses of Ethereum. Here are represented like M0 and M1, and we need to store them in A and B. And then we have the value that we want to update in the memory. In the ROM, we put this value in a variable called bytes to store. We will see it also. And in C, it's where we put this codification of how we want to insert this value in the memory. So the first parameter, it's the first one is the offset, the second one is the length, and the third one is the alignment. By default, the alignment is on right with the value of 0, and we will be storing the value in the left of the 32 bytes slot. And other way, if we put the value of this alignment as 1, it will be stored in the left. In case you are storing 32 bytes, obviously, the alignment left and right is exactly the same, so it doesn't really matter. And the same happens with the Indian type. If we put it as 0, by default, we use big Indian, and if we put it as 1, it's little Indian. This is the value that is updated in the memory. So the last register is the memalign write. In this case, we'll have to put the original value of the memory of the first slot that you are using to A and the second one to B, and the result of the memory after inserting the value to D and E. And the value that you want to insert is in the op. We will see. Maybe now it's a little bit difficult to imagine how it works, but we will see it in the code, and it will get far easier, although not that easier. Here, this is an example of how we've been doing the memalign before the optimization. The thing is that we wanted to read these 32 bytes, so we had to put the value of the first slot that we want to read to A, and the second one to B, and we can choose the offset, and we put it on C. As you can see here, these symbols mark the bytes that we want to read, and we start in offset 12 as we have set here in C. And when we do this memalign read, it will put the value of the read output on A. And with this assert, well, this is like a test. With this assert, we will see that indeed the returned value of memalign read, it's these 32 bytes that starts on 1C, like here 1C, and ends in like A3B. And more or less happens with the memalign write. But in this case, you have to put the original value of the memory on A of the first slot and the second slot on B, and the result value of the writing on D and E. And doing this last instruction, what we are doing is like asserting that indeed the stored value is this one, which is 0E1, and it starts like here also 0E1 and ends with 3Fs. So these tests they will have their correctness proved, and they will work. Another optimization is the arith mode. This one is very useful in the zkEVM for doing this easy recover and also for doing the mul mode opcode. Previously of this optimization, we were doing it like manually, the arithmetization with only the arith with the arith state machine. So it really get very more simplified. And here, this is an example of another useful usage of the modular arithmetic to compute the mode.
Thanks. Okay, so now let's get into the details a little bit. So now we are going to see some code, some zkAssembly. But first, I would like to explain a little bit the push opcode, how it works a little bit on the zkEVM. So, as I mentioned, we have kind of a buffer of bytes. This is basically hashed, and when you hash the bytecode, this is the hash bytecode that's introduced on the sparse Merkle tree. So imagine that we have this buffer of bytes, okay? And this buffer of bytes, it has on the zkEVM, it has some limitations. You can read this buffer of bytes, but you need to read it always in the same way. So if I'm reading from byte 1 to byte 3, I always need to write those bytes in the same way. I mean, I cannot read it again in a different way. Otherwise, the proof will be broken, basically. So since a bytecode, you need to interpret the bytecode, and we don't know where the pushes are, basically, we need to read the bytecode one by one. So, again, imagine that you have the bytecode, it's byte after byte, okay? You imagine a bytecode of a smart contract. And then, when you do a push operation, basically, you are getting a bytecode from the bytecode, and then you are inserting into the stack. So, here, we're reading push one. We are reading the first bytecode, the first byte of the bytecode of the smart contract, and then this will be added into the stack. Basically, the byte that we read is the, I would say, the less significant byte. Just for example, when we have 5 bytes, we are reading the first 5 bytes of the bytecode in case on a push 5, and then those bytes basically are saved in a register. This example is basically the register will be the final value, and this final value will be saved to the stack. Okay, this is a little bit how the push opcode works on the zkEVM. How we did kind of this performance test. So basically, we just kind of load some random bytecode in this buffer of bytes that represents the hash smart contract bytecode. And then we perform a lot of pushes opcodes. Okay. Of course, we assert that the result is okay. So for example, here we test the push 1. Basically, we are starting reading the bytecode from position 0, and we're reading 1 byte. So for example, here we are reading 0, 1. Okay, so basically we are doing here an assert in order to verify that the result is correct when we call the push 0. This case also is very straightforward. We are just reading 3 bytes from the very beginning. So the very beginning is the program counter. We are reading 3 bytes. We are calling the push. The read push basically is a generic function that reads as many bytes as are stored in the registers D and E. Okay, so here, basically the rule should be reading 3 bytes, 01, 02, 03. And in this case, this is a push 32. If we start at the 42 position, which is basically, okay, the first row are 32 bytes, so around here. Okay, we're starting around here to read. And how many bytes are we going to read? We're going to read 30 bytes, because we set here 32 in registers D and E, so this is the final result that we'll get on the final value. Okay, so, spoiler. The old implementation of the push, given those tests, consumes kind of a lot of steps. You can see that it consumes almost 6,000 steps. It consumes 278 binary state machines. And the new implementation of the push, it reduced dramatically the cost of the push opcode. As you may know, the push opcode is the most used opcode in the smart contracts, in Ethereum, basically. You can see that the reduction is amazing. It's a lot. So instead of consuming 278 binaries, we're consuming just only one. And the steps, we are getting 6x, basically, over here. Credits and thanks to Feli, the guy that is here on the presentation. Mostly of all of the optimizations we have thought about with him. And I think that I push him a little bit in order to do those optimizations. Let's see some code in order to check the push. How to check it? Okay, so let's start by reading the previous implementation of the push opcode. It's not easy to understand, and I will not get into the details because I would rather to go into the optimization one in order to explain it how it works. But basically, you can this push functionality in so many ways. So when we first code this functionality, we were thinking to code it in a way like you code it in Rust, in Go, or in JavaScript. So you need to do some kind of looping, some kind of for, you need to kind of shift right in order to accumulate the value, and so on. Here, it's not straightforward to follow again, but basically what we did here is we have all these bytes in the buffer of the hash. We are divided into 4 bytes blocks. Then we need to do some operation in order to compute, in order to do this kind of division. And then when we are reading from the very end, we are reading 4 bytes in blocks. We are storing those bytes into the final value. And at the very end, we are reading what I call here the left bytes. So you can have one block of 4 bytes and then 1 byte, 2 bytes, or 3 bytes. No? So we read first the blocks, we store it on the final value, and then we read the left bytes, and then we store it on the final value again. This, it's, I mean, if you think about in some standard language, this is quite trivial and straightforward to do. Just do one division, 1 for, and that's it. But when you go to the zkAssembly, it gets a little bit messy because, as I mentioned here, this first part, it's only the division, basically. Here, the read push block, basically, it's reading from in blocks of 4 bytes and storing into the final value. But in order to store into the final value without using arithmetics, state machines, and binary state machines, we do this trick of using the rotate left. But how many rotate left do I need to know? Well, again, another loop in order to rotate as much block as you have, depending on the index of the block. This is basically this code. And when we kind of end this first loop, we enter in another loop, which is the loop that reads the missing bytes, what we call before the left bytes, and then those bytes also are kind of shift it again in order to move it to the most significant bit. So here basically it's kind of a two loops, shifting right. Wow. I mean, it's a little messy. It's very generic, the code. It's a little messy. So it's consuming basically a lot of steps. Because every time that you do a loop, even if you do in JavaScript, in Go, in Rust, when you do a loop, you need to maintain the E, you need to do the for, E equal to 0, E equal to 1, E equal to 2, blah, blah, blah. So here, exactly, it happens the same. So you need to maintain a register in order to do the loop properly, check if it's 0, then jump to the other loop, blah, blah, blah. So here the trick was, okay, let's unroll the loop. So let's not do the loop. Let's unroll the loop. Then the code looks, let me find the code. Here. So then you can see that now the optimized code of the push looks very repetitive, but it's because we don't need to do some loops. The loops are unrolled, so we don't need to maintain a temporal variable in order to do again and again and again the same. So it's unrolled. That's why the code is very repetitive. So the code probably gets longer, but it's much, much, much optimized in terms of steps. So I will just do one example of this. I will do two examples, how to follow this function of the read push, optimized read push. So this is basically the internal, the inputs, which is D and E, which is the bytes to read. That's it. And then the output will be in the register E. Then what we are doing here is, okay, we are entering into the function, read push. Okay, how many bytes do we want to read? 1 byte. And this basically it's a jump to a specific code. This is a way to say that we want to jump to a specific line of code. In this case, the E, as I mentioned, is the number of bytes that we want to read. So depending on the E, we are going to jump on a different level. So if I want to read 1 byte, I will jump to the read push 1. If I want to read 2 bytes, read push 2, and so on. So imagine that we need to read just 1 byte. Then we will jump to the read push 1. Then we assign the program counter. The program counter, you remember that, is the program counter of the smart contract bytecode, the very beginning. So, and then we need to read just 1 byte. Perfect. Remember that the hash K instruction, as I mentioned, it was for writing bytes into this buffer of bytes. We have the smart contract, but it's also used not just only to write, but to read byte as well. It is used exactly in the same way. But instead of writing, you're reading. Okay, that's why here we assign the program counter to the hash post register. And then we jump to this level, the read push 1. In the read push 1, basically we are, as I mentioned, on the hash K, hash P, or hash S, the E, what we put here, it's basically a pointer to the, it's an identifier of the hash, okay? And here basically we are reading 1 byte from the, in the bytecode of the smart contract, we are reading 1 byte, and that byte we are storing it on the E, and then we kind of finish the function. This is quite straightforward, isn't it? So imagine that we are reading 2 bytes. And here it starts the tricky thing. So here we are doing, instead of jumping to the read push 1, we are jump to the read push 2. And here we are reading the first byte, which is the most significant byte. And then in the second line, we are reading the second line, the second byte. This second byte, since we are using the using this kind of the free input check functionality, assume free, we are loading that byte into the dollar here. In the same line, we are also shifting the first value that we read, the first byte, 256. And then we are just storing that value, well, 8 bytes, 1 byte, sorry. And then we are storing that value on E, and then we are returning. Okay, so we are reading first byte, then we read the second byte, and in order to store in the register E, we take the first byte, we shift it, and then we put here the second byte. Then we have kind of built the value that we return. Same happens with read push 3 and read push 4. And basically, this, since the most opcoded used in Ethereum is read push, basically read push 1, you can see that basically consumes very, very, very few steps. Then, if you have a push between 5 or 32, basically it jumps to a more generic way of reading bytes and store it into the stack. So, for example, imagine the example that I will explain is read push 5, for example, in order to make it short. Okay, so let's jump to this level, which is read push X. And basically this read push X. Okay, here, as I mentioned before, it's just an identifier of the hash that we want to read. Here it kind of initialize some variables because they will be using afterwards. And then here we are basically, I love this trick, but basically we are kind of jumping in a reverse way in order to accumulate the value properly of the hash that we are reading from the buffer of bytes. So here, for example, in the example, basically you can imagine that the E is 5, so the read push base table level is here, is this line. Then we are subtracting 5, so we are just jumping to 1, 2, 3, 4, 5, to this line here. And here, what are we doing? We are reading 1 byte, the first one. Here, as I mentioned, we have kind of initialized those registers. So in C, I will have the first byte that I have read on this buffer of bytes. Then I will read another byte. Remember that I have in C the first byte. Then in A, I will accumulate the next 4 bytes. And what we are doing here, the trick is that we are shifting one slot. I mean, we are shifting, you remember that a register is composed by 8 elements, so we are shifting one element of C, that remember that it has 1 byte, we are shifting to the left, and we are adding the A value. And then we have the final value in order to add it to the stack. You can do exactly the same example, but instead of 5, just imagine 15, 16, or whatever. Okay. This trick is very clever because it saves a lot of steps of the push off code, and the push off code is very used on Ethereum. And basically here we are using 2 techniques. The first one is the unrolling loops. So instead of doing the looping, you just do all the steps that you would do in a loop, so you don't need to maintain these temporary variables. And then we use also here this assume free instruction. Okay. Okay, that would be it. You want to explain more?
Okay, so the next thing I'm going to explain is the optimization of the mload X and mstore X. So Now we will go deeper on the code of how the state machine of the mema line works. But first, before optimizing this state machine, remember that I said that this state machine only was supporting as input 32 bytes. So what happened is that we had if we wanted to store a value with less than 32 bytes, we can choose the offset, but we cannot choose the length. So what we had to do is to read the current memory that is stored, start shifting this memory with the value that we want to insert to generate this 32-byte slot, and then use the mema line with this input. Here is an example of how we were doing it before to understand how overloading was doing it before the optimization. Imagine we want to store these bytes, it's 2Fs, that with an offset of 4 bytes. And in the current memory, we have this slot of 32 bytes with these all A's. So at the end, we want to put these 2Fs in offset 4, so we want to put them here. What we had to do is read the current memory, read all the A's, shift left, and an amount of 32 bytes minus offset minus the length, and shift right, so that we had this value in a register. After that, we need to get the other side of the value. So we all again took the current memory and we do it now the other way. We shift right and then we shift left. So we have this A and all zeros. And finally, we had to add the 3 slots. So we add this one, the bytes that we want to store, the shifted right ones, and the shifted left ones, and we get the result. And this is the input that we put to the mema line state machine. Luckily, now it's far more easy because we can choose the length that we want the mema line to prove. So we just had to give him the value, these 2Fs, say the offset, and say the length. Now let's see in the code how was done before and how it's done now. As you can see here, this function, the mStorage function, it's widely used among the zkEVM, and it's used when we want to store a value of less than 32 bytes in the memory. So it's used in a lot of codes. This is the not optimized code. As an input, we have the offset where we want to store the value, and we also have the length. And previously, I will not go line by line because this one is very, very long. But well, we always check first that we have enough counters to do this function. Here we are storing, like making a snapshot of all the register. As you can see, we are not using the save here because it's not optimized. We do some checks of the memory expansion, the gas, if it's correct to do this store. And here we start to do, jump to the mStorage 2. Here we do these shiftings that I've shown in the slide. It was a shift left and a shift right. And here we have the value in A. We shift left this value, then we shift right this value, then we make the addition, we shift right again, everything to obtain these 32 bytes that we want to insert in the memory. The case is that it was very, very, very tricky and it had like a lot of complexity. Also, shift right and shift left operations are very, very step consuming. And when we had this value that we want to store, it's on that moment that we were doing the mema line state machine here. As I've said before, we put the value of the first slot on A, the value of the second slot on B, and the resulting values on D and E. Here we do it with a free input. And finally, we do the mema line state machine. And with this mload, we are asserting that it has done correctly, that indeed it's inserting the bytes that we want to insert. And now we will see how is it when it is optimized. You will see that the lines have been reduced dramatically. We, the same way, check that we have enough counters. As you can see, we are only checking steps and memalign, and very few steps in comparison with the other. That, in a first view, means that it's very, very optimized comparison with the other one. We do this same length check, and here we use the save. So instead of using, I think it was 4 or 5 steps for snapshotting the register, we just do the save, and they are all stored in just one step. This function is super, super optimized. Actually, it uses some optimization that we have not explained yet that makes it a little bit more complex to understand. But, well, I'll try to explain line by line. As mStoreX, it's only used for trying to store memory of less than 32 bytes. Here we do this check. In case it's more than 32, we throw an error. And here, in this, I would say, like less than 20 steps, we are doing what we were doing before, like in, I don't know, 100. We use this free input. With this 0, we assure that this free input it's less than 32 bits, that it's storing in A. At least this, well, these are like the same checks that we were doing in the other version, but these one are optimized. Also, we check here that we're writing the memory in a lower slot than the maximum expansion bytes. The maximum expansion bytes, actually, it's a constant. We can check it. Yes, it's a constant. That is the maximum memory that you can arrive in the zkEVM or in any EVM with the 30 millions of gas that you can do in a Ethereum block. Here we do, it's like an optimized way to do the offset utils that we did before. Here, having the offset, we get in which slot and which offset inside the slot we are trying to insert this new value for the memory. Here we do some more checks, and finally, here, as you can see, we don't need to do any shifting because this new memalign state machine supports setting the length of the value that you want to insert. So any value lower than 32 bytes, it's supported. So the same way we insert the value of the first slot on A, the second one of the second slot on B, and by free input, we get the new value after inserting the value that you want to insert. And you do the memalign state machine. Now this is the new one. And with this MLO, we are checking that indeed the result that it's being inserted it's the one that we wanted to insert. So now I did like a test of memalign that it runs the same code to the not optimized function, and after we will run it with the optimized one. Okay, I have it here. Well, this README it's in the QR that we shared at the beginning of the presentation. First, we execute this test, and well, this test is doing some memalign state machines. She's calling the mStoreX, and as we can see, the non-optimized one it's spending like 12 arith, 7 arith, 12 binaries, 200 steps, and for the new one, it's only using one memalign and 25 steps, so the optimization is huge, and it really impacts a lot in how many transactions can be fit in a batch, and also this impacts a lot in the price of the transactions when you do it in the zkEVM. So now this seems like little optimizations, but they really make a very big impact in the pricing on the zkEVM, so in the compatibility in the zkEVM with other chains, so they are really, really important. So I think that will be everything from our side. Thank you very much for coming. A special thanks to Feli for his contribution on the optimizing the zkEVM. And well, hope you had out time, Carlos.
Thank you for being here. Any questions? Yes.
What's the effective impact on the prover? So when because you're obviously if you're saving 10x on the instruction sets, you're reducing the number of proofs that need to be generated by 10x, and that obviously amortizes across the entire supply chain from normalization, aggregation, etc.
Yeah. Basically, right now, what we have in the EVM, what we have, work? Yes? Oh, thank you. So, if you have kind of a push that consumes 1,000 steps, and in the prover side, you need to prove 1,000 steps, you will take, just as an example, 1 minute. But if you need to prove 100 steps, so the next less, basically, the time in order to generate that proof will be way less. Okay? That means that you need to rent, the infrastructure you need to rent in order to generate that proof also will cost you cheaper. And if it costs you cheaper, it means that the impact of the layer 2 transaction of the user also will be cheaper. Also, if you generate the proof much faster, you can aggregate in advance, of course, because you need to, when you finalize some proof, then you finalize another, and then when all the proofs are finally generated, then you start the aggregation phase. So, I mean, if you finish the proofs before, you will start the aggregation before as well.
You have less proofs to aggregate, right?
Yeah, of course. Exactly.
It makes a big difference if you're...
Yeah, exactly. So optimizing this meaning optimizing everything at the very end. Everything speeds up, everything it's cheaper, so it benefits not just only the prover, the sequencer, not just only the prover, but also the sequencer and the users. But it takes a lot of time to do those optimizations. It's not easy when you analyze the code and the offenders and the bottlenecks and so on.
Are you doing this by hand?
What do you mean?
So I would presume that you would, in order to, I would presume the code base is significant, right? I mean, how many lines of
How many? I mean, the ROM basically is an EVM implementation in zero-knowledge language. We did it by hand, so line by line. How many lines? I don't know. More than 1,000. Yes, totally. I think only the pairing. No, well, the pairing. I would not. It's very difficult. Well, we have some auto-generated code of the AC in the pairing that it's maybe 500 lines that Hector did. Modular exponentiation also is fucking crazy. More than 200 lines. If we left kind of aside the precompiled, which are kind of difficult to do on the ZK side, the rest of the code should be around 2,000 or 3,000 lines.
So
Yes.
I was just thinking it might be actually worth training an LLM on that.
Yeah, sure, totally.
No, I mean it's like as a might be actually worth doing that.
Yeah. I mean, for example, what we did is instead of going to the code manually and check if every line can be optimized, what we did is basically analyze some traces of some transactions in Ethereum that used to happen on Ethereum, like a Uniswap swap. Once we got those traces, we kind of built a ratio between how many times an opcode appears on that trace. I would say a DeFi trace, generic DeFi trace, and then understand the bottlenecks, and then we analyze the compiler and the code in order to perform better. That's why we put the focus on that specific opcodes, because those opcodes were the opcodes most used in Ethereum, most used in DeFi transactions, and they were the most offender of codes, the one that consumes a lot of steps, for example, and binaries and arithmetics. So we decided to put the focus, very focus on those opcodes. Thank you for the question. Anything else?
Actually, I have a very stupid question.
No.
Because I haven't looked at the code in a long time.
No.
Are you using so for the memory pools, right? The M load and the M store,
Yes.
right? Are you actually saving the code because the proof because on M load you actually probably you need a recursive proof, right? In order to prove out all the previous manipulations are correctly done, right?
Well, this basically happens on the proving side. So we have kind of the main state machine. The main state machine calls this secondary state machine, which is the memory aligned state machine. And in order to prove memory readings and writings, we basically sort all the memory, all the actions memory that we did, and then we prove that they are correct.
Yes, but I mean, if you're proving M load,
Yes.
right? You had a previous M store to that.
Yeah. That's why if you put all the M stores and M load in order, you will have the flow of a specific memory region. And we assure that it's okay on the proving side. If you have more questions about proving and how the state machines work, we have here the guys also that knows better.
It's actually on the first load, right?
Yeah.
The first load, not when you're actually in the trace. Right. If you have this one there, it's very easy to integrate that this array must be the previous array that you have. Well, that if you're in the instruction set, right? If you're loading the instructions from onto the stack, and then you're lining your memory based on the rewrite. That I completely understand. It's the initial one, right? When you load the very first value, or when you touch an address for the first value in the instruction set, right? You need to prove that the previous manipulation of that address was done correctly. Otherwise, you don't know, right? So it's like when I read for the first time, is EVM, we don't have manipulation, right? So that's why. So that's why I say that's the dirty little secret of
Okay.
zkEVMs. You're actually not, because everything is stateless except the memory manipulations
Well,
between
yes.
transactions. So if you're touching an address for the first time, you're loading that, right? Then you need to prove that whatever manipulation happened before was done correctly. So in principle, so you would have to carry the proof for that particular address to the last successful manipulation over, and then in the first proof for that, you recursively prove the previous, verify the
one thing that is important that is one of the control is done is that this list is already already sorted. That means that if you avoid or you cannot put a step before or after, because for this reason it's sorted by address and after by step. That means that if I make a read, it is the first read. That means what I sort is the first read after the other change. And after the other change, the situation is right, the value is position right. Is green, the value is 0 because not that any previous right of this others. I can show you in a
Yeah, we can do that. I don't want to. There's a one-third that you don't want to have to actually read a value from an address into the register.
Maybe we have like 1 minute for one more question, maybe, but very fast. I think
We can iterate later
we
on.
will talk later. Yes.
Yeah.